All right. Welcome everyone. Welcome back. Welcome back to Week 4 seminar. Today we're going to discuss the Boyer-Moore algorithm in string pattern matching. Um, yeah, and here's the author of this algorithm, Professor Strodemoth and Robert Boyer. Boyer was a professor at the University of Texas, and Boyer-Moore, he was on Wikipedia says he was an American computer scientist, and his career involved in MIT.
Maybe advance the slide on the other.
Sorry. Okay, so just a quick overview. As you know, last week we covered the Z algorithm in string pattern matching, and the key idea of the algorithm is we do a pre-processing over the pattern. So yeah, it would be very useful in furthermore in when we deal with the text. And the same idea applied to the Boyer-Moore algorithm. We need to do the pre-processing over the pattern, but in contrast to the ninth algorithm and the Z algorithm, we do the backward scan. So what do I mean by backward? We scan the pattern from the right to the left. And there are two main heuristics that can be independently used to process the text and the pattern, but we'll mainly cover the bad character heuristic. The other one is the good suffix heuristic. Yeah, but I'll mainly talk about the bad character heuristic today. Okay, so the reason why we need to do the pre-processing, there are various reasons. Yeah, you know, pre-processing allows the algorithm to make large shift in the pattern rather than just one position at a time, and this could help reduce the total number of comparisons needed. And besides that, the pre-processing could also allow us to, you know, the algorithm to quickly determine the optimal shift, so you can minimize the need to recheck characters that have already been compared. And also by using the bad character and the good suffix heuristic, we could skip sections of the text that do not need to be compared. Yeah, you know, if we have an example, if there are some characters in the text that doesn't appear in the pattern, so there's no reason for us to compare that at that position with the pattern, so we can skip all the way, go at the end. Yeah, and here comes the bad character heuristic. So the definition: for each character x, let Rx be the position of the rightmost occurrence of x in pattern, and Rx is defined initialized to be 0 if x does not occur in P. Yeah, and so the character of the text that doesn't appear in the pattern is called the bad character. And Rx needs to store an entry for each character in the alphabet, so the size of the R could vary, depends on whatever you need to deal with the problems. It could be 26 when you only deal with English alphabet, but it could be also extended to 256 when you're dealing with the extended ASCII. And it takes you constant time to assess particular elements in the R if you use a vector, or otherwise if you use order map or hash map. I'm not sure if you can make it in constant time. And it also takes you big O of n to construct table R, where n is the length of the pattern.
Sorry. So can you go on? So what's okay? So K here is like a character, right?
Yeah, K is a character
K is the rightmost place in
of
the
currents
pattern.
in the pattern of that text of a character in the pattern.
I see. But you have this for every possible character in your that might show up, not just the characters in.
Not just subware. So the main idea is we initialize this to be 0 if it doesn't occur in the pattern. So all the things, but honestly, I don't think that there's no point in doing that. But
So what's sigma here?
sigma is the size of the space complexity. You know, if you build only English alphabet, it could be sigma is just 26.
Sigma is like the number of possible
Yeah.
characters.
Okay. So let's take an example of the pattern. So the pattern concludes including three distinguished characters A, B, and C, and the rhyme occurrence of that characters in the pattern, as you can see here. A appears in the rightmost position as index 6, and YB is 5, and similarly for CE 3. Okay. And as the previous slide says, so only A, B, and C appears in the pattern, so R, D to Z would be 0. Okay, and if we have a look at the pattern and the text here, so the key idea is to compare the rightmost occurrence character of the pattern with the encounters in the text, and C and A here, they doesn't match each other. So the text S3 is C, mismatched with B3, and the R value of C in the pattern is 2. So the formula to shift the pattern is you take the maximum of 1 and I minus R at TK, why I is the position in the pattern that P where the mismatch occurs, and we always take the maximum of this difference and 1 because we always need to shift at least 1 position to the right, ensuring the pattern moves forward and the text doesn't stay in place. So if I shift the pattern to the right by 1 position, we could find a match here.
So what would you do if instead of a C in the text there was a D?
Okay, oh, I see. So if the text, if D appears in the text but it doesn't appear in the pattern, I would simply shift the pattern over past the D so that we don't need to compare any previous characters of the D. So yeah, it's
that's like a huge gain, right?
Yeah. So that's why the bad characteristic is. Oh, so honestly, when I did this slide, I wasn't really understand well about the algorithm. So So I just stop here. Do you want me to go over the text manually so that you can see how the algorithm works? I mean, so yep. And when we found a matching pattern in text, we simply shift the pattern. It could be 1. So in original Boyer-Moore algorithm says if you find a pattern and then you shift the pattern to the right by 1 position, that's the original thing. But when I do the research, I also see that we could optimize the shifting position by looking at the next character in the text, the next character in the text that appears right next to the A right next to the the A in the text, the matching character. So yeah, we could shift the pattern, and then in this case we shift to the right by 4 position. See, you guys see what I'm saying? Let's move on to pseudocode so that you could understand it very well. You see in the if statement, and if the pattern is found, and then that's how you calculate the shift. So the character in the text that comes immediately after the match segment is the text at position shift and then plus m, where m is the length of the pattern. And so the rightmost occurrence, the R of that character gives the position of the rightmost occurrence of the character in the pattern, and then you take the difference between them and tell you how much to shift the pattern so the character aligns with its rightmost occurrence in the pattern. Do you see what I'm saying? Okay, thank you. And and the running time. Although people often say that Boyer-Moore is a linear algorithm, but actually it isn't. But the worst case of time complexity is O of n times m, where n and m is the length of a text in a pattern. The reason for that is this can happen when the pattern consists of repeating characters, and the text is also built in a similar character, identical to the text. So the text that contains many substrings that but partially match the pattern but only differ in the last position. So that's why you have to do n times m comparisons to check every position in the text. But yeah, no need to worry about that because we rarely encounter this case in real life. So we could efficiently use this algorithm in patterns matching problems. Yep. So there are many applications of Boyer-Moore algorithms. The underlying algorithm of when you press Control and then F in such a particular user browsers, they often use Boyer-Moore. Why there are many similar algorithms to deal with Control F is the KMP, Z algorithm. I don't know, but it is said that Boyer-Moore is often used, mostly used. And one more example of Boyer-Moore algorithm is in DNA sequence analysis and plagiarism detection. Yeah, you have any questions? Any other questions? Thanks everyone.